Aha! Hey, peeps. All right. I'd like to introduce a slightly different case for relative velocity. Last time what we looked at were two cars, and one was ahead of the other by a displacement. There was a displacement that car 2 was ahead, and then we calculated the time at which car 1, the faster car, would meet car 2, and where they would meet. So we have a slightly different situation, even though the question is the same. The question is, at what position and time will car 1 catch and surpass car 2? The difference now is that car 2 has a 2.5 second head start. So how do we deal with that? So the situation is kind of like this. Car 1 and car 2 have the same starting line, so they have the same origin, same place where they begin the race. However, car 2, traveling at 2 meters per second, is given a 2.5 second head start. So it moves for 2.5 seconds, and it's going to be over here in this zone. And then car 1 will start its engines and will try and catch car 2. So how do we handle that situation? Well, again, we're going to do it a couple ways. I'm going to show you 2 ways. One is the graphical method. I'm going to hand that over to my avatar. And then I'll also show you the algebraic method, which is quite similar to the one which we did before.
And so here we are with the graphical method for the case where car 2 has a 2.5 second head start versus car 1. So what I decided to do is represent this in the following way. Time equals 0. Well, that's when car 2 will begin. And it has a slope that's obviously not as steep as car 1 because car 1 is going to overtake it. And we can see that the intersection is over here. So car 2 travels in this time before car 1 even starts. Here's where car 1 actually begins in time over here. We have this strange part here, this negative intercept. So it's kind of saying that car 1, the delay of 2.5 seconds over here, if it begins at 2.5 seconds, is almost like it would be at the negative 12.5 displacement location. And then it would finally reach the axis over here where we have the 2.5 seconds that we looked at for the delay. I can show you exactly in a moment when we interpolate. So if we plug in some numbers over here, we got 2 meters per second for velocity 2 relative to the ground. And over here the equation looks kind of interesting because we've got the slope, which is the velocity of car 1 relative to the ground, in parentheses times t minus th. So this is the offset. This is the delay. Th represents the delay in time that car 1 will get going. And so that's 2.5 seconds over here. So we have 5 meters per second times, in parentheses, t minus t delay, or you can view it as head start in terms of car 2. All right, if I turn on the interpolator, we can get some values over here. Let's make this slightly bigger for us so that we can see it. How's about 36? That would work for me. Will it work for you? We'll find out. Yeah, plenty big. All right, so over here we can see the time is 2.5 seconds. That's when car 2 begins. And over here is the intersection. And notice it's about the same place. It should be 8.33 meters relative to the origin where each of the cars began in this case. The time is a little different, 4.17, 4.16, somewhere in there. Remember before we had 1.66 seconds? Okay, well, in this case over here, we have that plus the 2.5 second delay. So one way to think about it is that this 2.5 seconds, how far will car 2 go in 2.5 seconds? It goes 5 meters. That's essentially its head start. So we were looking at it from the perspective of the y-axis right here, where my cursor is right now, and the intercept was 5 meters. So there's a few ways to look at this even graphically. Next, I'm going to show you the algebraic method by setting the offset for car 2 and giving it a head start in time.
So the algebraic method for the two cars, one with the head start of 2.5 seconds, okay? So here's the deal. Hey, guy, All right, this is the other dude. That's Mish. All right, say hey to Mish. He's hanging out too. All right, we have d car 1 is the same as before. v1g, so it's v1 relative to ground times t, but now d car 2 has v2g, and what I'm going to do to model this equation that you saw before in the graphical method is put this in parentheses. So we have the t from before, it's the variable, so as t increases in time, this changes, but th, h stands for head start, h is going to be constant, that's that 2.5 seconds. So what I did here is I just distributed this out, v2g times t plus v2g times t head start. Here's something that's kind of interesting. If I analyze this here, analyze the units, well the units for this velocity are meters per second and seconds. Alright, so the seconds cancels out and we've got meters. This is kind of like our new distance head start, so we can kind of translate that over and you'll see it carried through. Alright, so as we did before, we set displacement of car 1 and displacement of car 2 to be equal. We solve for t. And over here, we've got v1 g times t, v1 g times t. Now this is the expression that changes. Instead of dh as it was before, it is v2g times th. That whole expression from before. All right. So everything looks exactly the same as it did when we did this problem the first time. The only change is that we have these terms. It's in terms of th, the time, and v2g. The final expression is very similar. Instead of dh, we just have these two terms. And check it out. I have th is 2.5 seconds. All right. So what that means is when we put it up here, we get 2 times 2.5, which is, hey, guess what? It's 5, just like we had before, 5 meters. So actually the head start was 5 meters. So it's really the same problem. I just encoded it a different way. I coded it in terms of the time head start from the origin. And we actually get the same result. So 1.66 seconds and 8.3 meters. You know what? This got screwed up from last time. Isn't that funny? I caught that now, but it wasn't caught before. Maybe you recognized it. Maybe you saw it. Let's fix it. All right. So that was my bad. 8.3 meters. See what a day does? You get to see something fresh and new. All right. And that's what that was Mish over here. That's exactly what he was trying to tell me, that I had the units wrong. Thank you, man. All right. So with that, Morad, Mish.